In section 5.6, we're going to be solving exponential and logarithmic equations using some of the laws that we've learned about in the previous sections. So we're going to start by looking at these two examples and solving each one. So in the first one, if you remember from the previous section, we want to try to get the same base. And we know that 9 is 3 squared raised to the x and 3 to the x minus 1. And so we know that is 3 to the 2x, and this stays the same. So from here we can say, since we have the same basis, we can say that 2x is equal to x minus 1. And when we solve that, we find out that x is equal to negative 1. All right. The second one is a little bit harder because when you try to get the same basis, you notice that 6 is 2 times 3. And that's not going to work. We're not going to be able to get the same basis, so we need to try something else. So maybe we'll try taking the natural log of both sides. And so when I do that, I get this, and then I can take my x, move it out front, and then divide both sides by the natural log of 6. And I'll need to use my calculator on this one to find out that x is going to be approximately 0.6131. Okay. Okay, next example, again, you notice you have a base of 4 and a base of 5, so there's no way for us to get the same basis. So these are getting a little bit harder, and that will continue as we get through the fourth example. So since we can't get the same basis, let's try to take the natural log of both sides like we did in the last example. Okay, that's going to allow us to pull our exponents out front, and we get okay. Now at this point, what you need to realize that you can do is that natural log of 4 and the natural log of 5, those are just numerical values. So that's going to be distributed just like we distribute a 4 if it were there, here and here. Okay. And once we do that, we end up with 2x times the natural log of 4 minus natural log of 4 is equal to natural log of 5 minus x times the natural log of 5. Okay. At this point, you should recognize that you have an x on each side of your equation, and the idea is to get is to isolate x. So what we want to do is get all of the x's or all the terms involving an x on one side and all the constants on the other side. So I'm going to keep my 2x natural log of 4 here. I'm going to add my x natural log of 5 to both sides. I will move my natural log of 4 over and keep my natural log of 5 on the right side. And so I end up with this. And again, I want to isolate those x's. Okay. And what we have is a sum, and each of those sums, each of those terms has an x. So I can factor out the x, and when I do, I get this. Okay, and from here, I want it to solve for x, so I'm going to divide by and then we're going to need to use our calculator to find the approximate value of x. And be careful when you use your calculator. You're going to need to make sure that your calculator puts parentheses here and here. Let's do that in a different color. Your calculator is going to use parentheses here and here, here and here. In addition to that, you need to put parentheses there. Be sure to use these parentheses, and then of course it puts the parentheses here for you. Okay, and when you do that, you end up finding out that x is approximately 0.6836. Okay. All right, now let's look at our next example. And again, this one gets a little bit a little bit more complicated here. So this time you notice that you have several terms with an e in it. If you took the natural log of both sides this time, it's not going to really help us because we have that difference there. So we want to try to think about this one a little differently. You notice that you have an x here and a negative x, and we could almost sort of see how this one begins to look a little bit like a quadratic equation where you have the x squared plus x plus a constant here. So how could we make that so that this is more like the squared here? And the answer is going to be to take the entire equation and multiply it by e to the x. Okay, when we do that, we're going to distribute this in here and to the 6, to the negative 6, and that ends up with e to the x times e to the x, which is e to the 2x. Minus 5e, and then you got e to the negative x times e to the x. Those just cancel out, so we end up with minus 5 equals negative 6e to the x. Okay, so once we're there, we're going to get everything on one side of our equation. And try to factor this. And in an attempt to factor this, you realize that it won't factor because you have a negative 5. You want it to get a positive 6. So we have to use a quadratic formula. But it might be easier to think about this using the quadratic formula if we let u equal e to the x. And then it's going to be a little easier to understand. So if we let u equal e to the x, then what we're going to have is u squared plus 6 times u minus 5. And now you can see why we can use the quadratic formula here. Okay, so x is going to be equal to our negative b plus or minus the square root b squared minus 4 times a times c. And that's going to be over 2a. And when we simplify this, we end up with negative 6 plus or minus the square root of 56 over 2. And let's continue to simplify that square root 56. And when we do, we get negative 6 plus or minus 2 root 14 over 2. And every term there has a factor of 2, so we can simplify that and get negative 3 plus or minus the square root of 14. Okay, so if you go back and look at the original, so we've got basically what this is going to produce is produce a negative number and a positive number, okay? So if you were to be negative, or if what we know is that e to the x must be positive, okay? So let's see. So now if we substitute back in, this is, keep in mind this is what u is equal to, right? And u is e to the x. So let's replace that. So we have this plus or minus 14. Okay. Now what I'm trying to say here is e to the x, this right here is always going to be a positive value, okay? So that means that we don't need the negative result here. We just need this. Okay, so e to the x is that. And remember that we want to know what x is. So how do we then solve that? And the answer is going to be, then we take the natural log of both sides. And when we do, we end up with this. Okay, and again, I got this by bringing my exponent out front. And so the natural log of e is just 1, so x is going to be the natural log of this quantity here. And use my calculator, and I'll find out that x is approximately 0.2989. Okay? All right. Next, we're going to go back to the word problems that we've seen earlier in the chapter that we only solved graphically, but now we're going to try to solve those algebraically. So in this one, you've got $8,000 and it's invested at 6% per year. It's compounded monthly, and we want to know in how many years it will take the investment to be worth $22,520. So what we want to end up with is the $22,520. We started out with the $8,000. This is going to be compound interest, so it's 1 plus our rate, which is 0.06, over the number of times compounded per year, which is 12 in this case, because it's compounded monthly, and raised to the number of times compounded times the amount of time. T is what we're trying to find here. Okay, so we just need to begin simplifying this. So if I start here, what I want to do, remember, is to isolate this t here. So how do I get the t by itself? Well, right now it's an exponent, and we need to find some way to get it down. The only way to really do that is to solve when you have an exponent as your variable. Is we know that we're going to be using logarithms, but let's see how far we can simplify that first. The first thing I'm going to do is divide both sides by this 8,000. And when I do that, I end up with 2.815 is equal to, and then I'm going to simplify the 1 plus 0.06 over 12, and that gives me 1.005 raised to the 12t. Okay. Now from there, you can see that we have this t that we still need to solve for, but it's much simpler. So what I'm going to do is take the natural log of both sides. And the reason I'm doing that is because I have a variable as an exponent that I need to solve for. And you'll notice that by doing this, it allows me to take this and move it here, which is no longer an exponent, and that was the goal. So now I have the natural log of 2.815 is equal to 12t, the natural log of 1.005. And now I can divide by anything I don't need. Okay, these cancel, and use our calculator to find out that t is going to be approximately 17.3 years. Okay. All right, another word problem here. We've got the population of a certain species of a rabbit increases exponentially according to the function S of t is equal to p times e raised to the rt. P is going to be the initial population. R is the continuous growth rate. This is going to be a 12-month study, and 50 rabbits. At the end, we started with 50 rabbits, and at the end of the study, we ended up with 164 rabbits. So the first thing we want to do is to write a function for this. And to write the function, you have to remember we ended up with 164 rabbits. We started with 50, which is our P. E, we don't know what the rate is, and this is after 12 months. So you could do one of two things. You could do the 1 year, or you could do this monthly and do the 12 months. And so let's go with time being 1 year. And so if we have that, what we're trying to find here is the rate, the continuous growth rate. So that means we need to solve for that r that we have here. Okay, so we're trying to solve for this guy. Again, he's in the exponent, so that should tell you that we're going to use logarithms. So let's simplify as much as we can before we do that. Divide both sides by 50, and when we do, we get 3.28 is equal to e raised to the r. Now, you see that e in there, so that tells you instead of using logarithms, it's going to be best for you to take the natural log of both sides. And again, we're doing this because we want to solve for we want to solve for a variable that is now located as the exponent. So now that can come here, and it's very convenient that the natural log of e is 1. So we have the natural log of 3.28 is equal to r times the natural log of e, which is just 1. Okay, so we can use our calculator, and we find out that the natural log of 3.28 is approximately 1.1878. Okay, so now that we know what r is, we can write our s of t is equal to our starting with 50 rabbits, e raised to the 1.1878 times the amount of time. Okay, so that's part A. All right, and then in part B, what we're asked to do is find out when the population is going to reach 1,000. So we want 1,000 rabbits, and our formula is going to be 50 e raised to the 1.1878 t So again, simplifies for we're trying to find the value of t, so we divide both sides by our 50, and that's going to give me 20 is equal to e raised to the 1.1878t. Again, we're trying to solve for that t, so it's right now it's an exponent, so we need to bring it down. So I'm going to take the natural log of both sides. So I end up with the natural log of 20 is equal to the natural log of e is 1. Um, and so then and natural log of e again is just 1. Okay, it's 1. It's the same as 1. Okay, so I'm going to divide both sides by the 1.1878. And I don't need to worry about this because it's 1. And when I do, I find out that t is approximately 2.522 years. And you could also convert that to months, since the original was given to you in months. Okay, we've got one more word problem here. You've got a population of certain bacteria culture at time t hours is given by this function f of t here. And what we want to know is how long it's going to take the bacteria population to reach 8,000. So we want 8,000. So that's going to be our f of t is equal to 20,000 over 1 plus 20 e raised to the negative t over 3. Okay. So from that, what you notice is that you have a variable that you're trying to solve for, which is our t, that is an exponent, but not only that, but it's in the denominator. So we need to try to work through that and bring it to the numerator first, and then worry about getting it out of the denominator. So I'm going to make this 8,000 over 1. And we know that we can use cross products for this, okay? So if I use cross products on that, then I can say, since you have an expression that's equal, then you know that or you have an equation, then you know that the cross products of this is equal. So I can say my 8,000 times my 1 plus 20 e raised to the negative t over 3 is equal to 20,000. All right. Now I'm solving for t. It's in the numerator now. That's great. Solving for t, so let's try to work towards isolating it. So I'm going to divide both sides by 8,000. Those cancel. 1 plus 20 e raised to the negative t over 3 is equal to 20,000 divided by the 8,000 is going to give me 2.5. Okay, and from there I can subtract the 1 from both sides. And when I subtract that 1, cancels here. 20 e raised to the negative t over 3 is equal to 1.5. Again, working towards isolating the t, so I'm going to divide both sides by 20. And when I divide both sides by 20, I end up with e to the negative t over 3 is equal to 0.075. Okay, and now it's time to deal with that t that we're looking to solve for. So we're going to take the natural log of both sides, and at the same time I'm going to bring this negative t over 3 out front. So we should be pretty good at that by now. Natural log of 0.075. So I sort of skipped a step there. The natural log of e is 1. Okay, so remember that this right here is 1, which is convenient. And so what I end up with is that negative t over 3 is equal to the natural log of 0.075. And I need to multiply, I need to solve for t, but that's going to leave me with negative t. So why don't I think about taking that negative, and I'll just make that -3. It's the same thing, okay? Um, and I can multiply both sides by -3, and those cancel. T is going to be approximately 7.77 hours. Okay, and that's it. Next problem, not a word problem, but it is going to require a significant amount of work here. We're trying to solve for x. And if we're trying to solve for x, then what we want to do is try to get each side to a single logarithm so that we can eliminate those logarithms, okay? So in this one, I've got the sum of two logarithms, which means that I can rewrite it as the natural log of 4x minus 1 times x plus 2 equals, and I'm going to write the natural log of x squared here, okay? Now that I have the natural log, I've got an equation here, and on each side I have a single logarithm. So what that means is if I'm taking the log of something and it's equal to the log of something else, then that means that these two here have to be equal. So 4x minus 1 times x plus 2 is equal to x squared. And I'm just solving this. So I need to multiply this, 4x squared plus 8x minus 2 is equal to x squared. And let's move the x squared over and end up with 3x squared. And we're going to either factor to solve or use the quadratic formula. All right, a quick look at it and you realize that it cannot be factored. And so if it can't be factored, then I'm going to use the quadratic formula. So we've got negative b plus or minus square root b squared minus 4 times a times c over 2a. Okay, end up with that. Simplify and we get negative 7 plus or minus the square root 73 over 6. And we know, going back to look here at the beginning, so you've got, basically it's going to produce, if you plug that in your calculator, it's going to produce a positive, one positive, and one negative. Now if you go back here, remember that the domain, when you're working with the domain of natural logs, then it has to be, this value here has to be greater than 0, okay, in each of the instances. So I've got 4x minus 1 is greater than 0, which means x is going to be greater than a fourth. In this one, it means that x is greater than negative 2. And then in this one, it means x is greater than, not greater than, it means x is greater than 0. Okay, so when you're looking at your solutions, you have to go back and look at your domain. So which one is the, you go with the one that is going to take care of all of them. Okay, so x is greater than a fourth. So if x is greater than a fourth, then it's going to be greater than negative 2, and it's going to be greater than 0. All right, so we know x has got to be greater than a fourth. So we go back and down and look at our solutions. That means that the negative value would not work in this case. So we know that x is just going to be equal to negative 7 plus square root of 73 over 6. Okay, and that's going to be our solution. All right, last problem here. Again, we're trying to solve for x. And if we're trying to solve for x, then what we want to do is we want to somehow see if we can combine our logarithms, make a single logarithm, and then maybe isolate those in this case, since we have an 8 there that does not have a logarithm with it. Okay. The other thing you could do is insert natural log of, natural log of e, so that it is a logarithm. But let's start out with not doing that first. Let's move this to both sides. Okay, and when I do that, I end up okay, so then I can rewrite that, and that's going to, so I have the sum of two logarithms, or two natural logs, so I can write it as a single logarithm, and multiply the 2x plus 1, which is going to give me 2x plus 1 quantity squared is equal to 8. Now that it's here, I have a natural log on one side and a constant on the other, then that should make us think, okay, let's rewrite this in exponential form. So I've got my base of e here, raised to the 8, is equal to 2x plus 1 quantity squared. Okay. I want to solve for x, so what I would do is take the square root of both sides. So when you take the square root of both sides here, you got to remember to do plus or minus. But is e to the 8th ever, what's going to happen is that this is never going to actually produce a negative. So you only need to deal with the positive here. So just the square root of e to the 8th. And when you do that, you're going to end up with e to the 4th. It's equal to 2x plus 1. And then we're just solving for x. So I'm going to subtract 1 from both sides. And e to the 4th minus 1 is equal to 2x. I divide both sides by my 2. And when I do that, I just need to simplify. And I find out that x is going to be approximately 26.7991. Okay, and that's the last problem for section 5.6.